Hi folks, this time we're going to talk about the relationship between linear and angular velocity. This equation, tangential velocity equals radius times angular velocity, is very, very handy if you are trying to convert between an angular velocity and a straight line linear velocity. If you recall, we talked about the fact that if you've got an object that's undergoing some sort of a centripetal force, it's rotating around a circle. If you would remove that force or cut that string as this object is going around, it is going to travel off at a straight line tangent to that circle, and that is going to be that tangential instantaneous linear velocity. Now, as of course the object moves, that velocity's direction is going to continuously change. But if an object has a steady angular velocity, the value for the tangential velocity will be the same. Direction, of course, is constantly going to be changing, but the number will be the same. Meters per second for a velocity. Radius is going to be in meters, and angular velocity is in radians per second. Let's do a problem. Oh, before we do the problem, let's talk about what this actually means. There's a cool little relationship here, that velocity is directly proportional to radius. And what that means is if you've got a solid thing like a carousel or a rigid disc, and this thing is rotating around in a circle, whatever is close to the center and has a small radius is going to have a relatively small r. But if this is all connected together, as the radius gets a little bigger, velocity is going to get bigger. And as the radius gets a lot bigger, velocity will get a lot bigger. So the larger the radius, the faster the instantaneous tangential velocity. So there's a couple cool implications of this. Let's start with a carousel. Let's say you were taking your wild and crazy little nephew to the carousel, and this little 4-year-old had the need for speed, and you want to give this kid the most excitement you possibly can. If I'm going to call this horsey A and horsey B and horsey C, which one of these horses would the little kid ride in order to have the greatest experience of speed? Well, this one has the smaller radius, and so it's going to have a smaller tangential velocity, a little bit bigger, and put the kid on the outside horse, and he's actually going to experience more the same angular velocity. That's going to be the same, but the tangential velocity is going to be larger on the outside compared to the inside. Now, because of this, tangential velocity is radius times angular velocity, one of the cool things it affects is where we launch rockets from. NASA is located down in the Cape Canaveral, Florida area, and the question is why? Why in the world Florida, as opposed to the middle of the country, Nebraska, Wyoming, somewhere in here where it would be more logical to protect it from our wartime enemies and things like that? Why in the heck Florida? I always thought when I was a kid that they just plain liked warm weather, and that's why they went down there. But there is a really good reason to do that. If you look at a map of the United States, Florida, for the continuous 48 states, Florida is the furthest south. There's a little bit of South Texas, but Florida and South Texas are really similar, and this is one of the reasons why there is a Houston space station as well. Now, what's going on here is, if this is a top view, and this is the North Pole, and you were to look at the Earth from the top of the Earth going down, and this is going to be a little bit sad. Forgive me, everybody who lives in Maine. I'm going to make your state, the United States here, this is an upside down United States, where this is Maine, this is Florida, this is Texas, and this is Southern California. Yeah, I know it's hard to understand, but as the Earth rotates, the closer you are to the top of the ball, you are going to have a smaller tangential velocity. So anything that would be launched from Maine would have a smaller tangential velocity. Anything that is closer to the equator, which is Florida, is going to have a much larger instantaneous tangential velocity. So what that means is our rockets get an actual boost from the rotational rate of the Earth. The Earth rotates at the equator somewhere around 1,000 miles per hour, and that gets a little bit less as you go further and further north. Launching rockets from the North Pole, we would not get that advantage. But as you get closer to the equator, you get much bigger rotational tangential velocities. Here's a trivia question for you. Where does the European Space Agency launch from? Now, these countries are part of the European Space Agency. A lot of them have come together to launch rockets, etc., because there are a lot of small nations, and so hence they can pool their resources. Everything from Ireland, Switzerland, France, Italy, Portugal, Spain. So where the heck do they launch from? Knowing that closer to the equator, you're going to have a better shot of having more tangential velocity. Now, I've had a lot of students in the past say, hey, I bet they launch from Portugal and Spain or Italy, because those are the points further south, but they don't. The actual point that they launch from is French Guiana. There is a little protectorate of France down in South America that is called French Guiana, and all of these European nations come together and actually launch there. Now, we launch from up here, and the equator is this red line right there. So French Guiana is actually just a smidge below the equator, and Cape Canaveral, Florida is up like that. So what's the advantage of launching from French Guiana? Couple. One, if they launch over the Atlantic Ocean, it's safety. Once in a while they lose a rocket, and if they're going to have one that's going to be lost, it is much nicer to actually lose it over the Atlantic, where there's very low chance of causing damage on the ground to the civilian population. The other advantage is the closer you can get to that equator, it's that extra about 1,000 miles an hour. You don't have to produce with a rocket. You are shooting it off of a ball that's spinning at 1,000 miles an hour, and it takes a lot of energy to accelerate a mass up to a high velocity. And so it is to the advantage of the space agencies. All right, let's do a problem involving velocity is radius times angular velocity. Let's say you're riding a stationary exercise bike. The meter on the cycle indicates that the wheel is rotating at 9.1 radians per second. The wheel has a radius of 0.45 meters. How far would you ride the bike, X, if you rode for 35 minutes? All right. We can use this equation to find the tangential straight line velocity that would be equivalent to riding this exercise bike. So the tangential straight line velocity is going to be radius times angular velocity, so 0.45 meters, angular velocity of 9.1 radians per second. And when I do the math on that, I end up with 4.1 meters per second. Now notice, meters over seconds and radians blink out of existence. Kind of annoying, but that is what radians just do. They appear and disappear. You've got to keep your act together to know what's going on. In order for us to find displacement, I'm going to use the simple equation for average velocity, change in displacement over time, or x is going to be velocity times time. My straight line velocity, 4.1 meters per second, times my time, but I've got 35 minutes. Oh, I can't mix minutes and seconds, so I'm going to have to do a little converting. Get rid of minutes, keep seconds, 60 seconds in 1 minute. So how much time is that? 2,100 seconds. So times 2,100 seconds. Seconds will cancel seconds. The distance is going to be 8,610 meters. And it says they want to know what this answer is in miles. Okay, we can do that. So let's get ourselves a wee bit of room up here and go back to my ink. 8,610 meters, and there are 1,609 meters in 1 mile. So if you've done this, how many miles have you actually gone? I got to pick up my calculator. 8610 divided by 1609, 5.35 miles. That's not too shabby. All right, see you next time.